Tonight, we're going to talk about the places where stars are born. Not the stars themselves, not those ancient furnaces that have burned for billions of years, steady and familiar, pinned to the same positions in the sky your grandparents knew. We're going somewhere quieter than that, somewhere darker. We're going to visit the nurseries, the cold, hidden chambers of gas and dust where new suns are still taking their first slow breaths, where worlds are just beginning to imagine themselves into existence, where the raw materials of everything you have ever touched are being gathered and shaped in ways we're only now learning to see. These places have names that sound like they belong in old star atlases: the Serpens Cloud, the Chamaeleon Complex, the Rho Ophiuchi region. They are vast. Some of them stretch across distances that would take light itself years to cross, and yet for most of human history they were invisible to us. They do not glow. They do not announce themselves. They are made of the same darkness that fills the spaces between the stars, and for a very long time we could only guess at what was happening inside them. But something has changed. A telescope is now watching these clouds with eyes that can see what ours cannot. Infrared light, the kind of glow that cold things emit, the kind of warmth that seeps through dust the way candlelight seeps through a closed hand. And what this telescope has found in just the past few years has begun to quietly unravel things we thought we understood. The chemistry is not quite what we expected. The timing is off. The neat, orderly sequence we imagined, gas collapsing, star igniting, planets forming afterward in a predictable dance, turns out to be more tangled, more simultaneous, more strange than the textbooks ever suggested. What does it mean when the observations no longer match the models? What happens when we look more closely at the very first moments of a star's life and find that we have been telling the story wrong? By the end of tonight, you are going to understand exactly what the James Webb Space Telescope has seen in these molecular clouds, why the old picture of star formation is quietly falling apart, and why the truth, the real story of how suns and planets begin, is far stranger and far more beautiful than anyone predicted. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. The story starts, as so many stories do, with a question that seemed to have an answer. For most of the 20th century, astronomers believed they understood, at least in broad strokes, how stars were born. The process seemed elegant in its simplicity. Somewhere in the galaxy, a cloud of gas and dust, mostly hydrogen, with traces of heavier elements mixed in, would begin to collapse under its own gravity. Perhaps a nearby supernova would send a shockwave rippling through the cloud, compressing it, nudging it past the threshold where gravity could take over. Perhaps the cloud would simply grow dense enough on its own, over millions of years, until some invisible tipping point was crossed. Either way, once the collapse began, the rest seemed inevitable. The cloud would fall inward, spinning faster as it shrank, the way a figure skater spins faster when she pulls her arms close to her body. At the centre, the gas would grow hotter and denser, squeezed by the weight of everything falling toward it, until eventually, after perhaps 100,000 years, perhaps a million, the core would reach temperatures hot enough to ignite nuclear fusion. Hydrogen atoms would begin to fuse into helium, releasing energy, and a star would be born. Around that newborn star, the story continued. There would be leftovers, a spinning disk of gas and dust that had not quite made it into the star itself. And from that disk, over the next few million years, planets would slowly coalesce, grains of dust sticking together, pebbles growing into boulders, boulders crashing and merging until eventually whole worlds emerged. It was a beautiful story. It was a logical story. And for decades it seemed to explain what we could see. The young stars surrounded by glowing disks, the older stars with fully formed planetary systems, the progression from chaos to order that seemed to unfold across millions of years. But there was a problem. The problem was that we could not actually see the earlier stages, the very beginning of the process, the moment when the cloud first begins to collapse, when the protostar is still hidden deep inside its cocoon of dust, when the disk is just beginning to form. All of that was invisible to us. Optical telescopes, the kind that gather the same light our eyes can see, were useless. The dust was too thick. The light could not get out. We were trying to understand the birth of stars by looking only at the survivors, the ones that had already emerged from their nurseries, already cleared away the dust, already begun to shine. It was like trying to understand human childhood by studying only adults, piecing together what infancy must have been like from the faded memories and scattered photographs of people who had long since grown up. And so, for a very long time, the earliest moments of star formation remained a kind of darkness we could only theorize about. We built models, we ran simulations, we made educated guesses based on physics and chemistry, and the few clues we could gather from the edges of the clouds. But the heart of the process, the actual birth, remained hidden. Until now. The James Webb Space Telescope launched on a winter morning in 2021, carried into the sky by an Ariane 5 rocket from a launch site in French Guiana. It had been decades in the making, a collaboration of thousands of engineers and scientists across multiple space agencies, a project that had survived budget crises and technical setbacks, and the kind of doubt that accumulates around anything that takes too long and costs too much. By the time it finally left the ground, there were people who had worked on it for their entire careers, who had grown old waiting to see if it would work. The telescope travelled for a month, unfolding itself as it went, a sunshield the size of a tennis court, a mirror made of 18 hexagonal segments coated in gold, instruments designed to detect the faintest infrared glow from the coldest, most distant objects in the universe. It settled into an orbit around a point in space called L2, about 1 million miles from Earth, where it could keep its back to the sun and its instruments permanently cold, permanently dark, permanently ready to listen for light that had been travelling for billions of years. And then it began to look. In the years since, the telescope has sent back images that have rewritten our understanding of the early universe, of distant galaxies, of the atmospheres of planets orbiting other stars. But some of the most quietly revolutionary work has been much closer to home, not billions of light years away, but a few hundred. The telescope has been staring into the molecular clouds of our own galaxy, peering through the dust that had always blocked our view, and for the first time we are seeing what happens at the very beginning. The Serpens cloud is one of the places it has looked most closely. It lies about 1,000 light-years from Earth, in the direction of the constellation Serpens the Serpent. To the naked eye there is nothing to see there, just the faint scatter of distant stars no different from any other patch of the Milky Way. But in infrared light, the cloud reveals itself as a vast dark structure, a region where the dust is so thick that it blocks the light of everything behind it, where the temperatures are so cold that molecules can form and survive, where the conditions are just right for gravity to begin its slow, patient work. What the telescope found there, in the deepest images ever taken of a star-forming region, was not quite what anyone expected. The first surprise was the jets. Young stars, we have known for some time, produce outflows, streams of material that shoot away from the poles of the forming star, perpendicular to the disk of gas and dust that surrounds it. These jets are thought to be a byproduct of the accretion process, a way for the system to shed angular momentum, to release energy, to keep the whole thing from spinning itself apart. We had seen hints of them before, in other observations, in other wavelengths, but the Webb images revealed them in stunning, almost startling clarity. In the Serpens cloud, the telescope captured dozens of jets, narrow collimated streams of gas stretching for light years, punching through the surrounding cloud like needles through fabric. Some of them were straight and steady, suggesting that the young star at their source had been accreting material smoothly, predictably, for thousands of years. But others were kinked and curved, twisted into shapes that spoke of a more turbulent history. Episodes where the star had swallowed material in bursts, where the accretion had been uneven, where something had disrupted the steady flow. The jets were also, in many cases, remarkably young. The telescope could trace them back to their sources, tiny glowing knots of infrared light, barely visible even in these deep images, still so deeply embedded in the dust that they had not yet begun to shine in optical wavelengths. These were protostars at the very earliest stages of their formation, objects that had been collapsing for perhaps only a few tens of thousands of years, still gathering mass, still pulling material from the surrounding cloud, still years, perhaps hundreds of thousands of years, away from igniting fusion and becoming true stars, and yet they were already producing jets, already shaping their environment, already sending streams of material out into the void, carrying with them the chemical signatures of everything that was happening in the innermost regions of the forming system. This was unexpected. The old models had suggested that jets should appear later in the process, after the protostar had already accumulated most of its mass, after the disk had settled into a stable configuration. But here they were, erupting from the youngest objects Webb could detect, as if the very first act of a forming star was not to gather itself quietly together, but to reach out and touch the darkness around it. The second surprise was the ices. Deep in the cold heart of a molecular cloud where the temperatures hover just a few dozen degrees above absolute zero, certain molecules can freeze out of the gas and cling to the surfaces of tiny dust grains. Water ice is the most common, the same substance that fills your glass, that falls as snow, that covers the poles of Earth and Mars and the moons of the outer solar system. But there are others: carbon dioxide, carbon monoxide, methane, ammonia, and a whole suite of more complex organic molecules, the building blocks of the chemistry that will eventually, in some systems, give rise to life. Before Webb, we had only indirect evidence of these ices. We could see the absorption lines in the spectra of background stars, the subtle dips in brightness where the light had passed through the cloud, and some of it had been absorbed by the frozen molecules clinging to the dust. But the observations were always averaged, always blurred. We could say that ices were present, but we could not say exactly where, or in what quantities, or how they were distributed across the cloud. Webb changed that. Its instruments were designed to take spectra of individual points within a cloud to map the chemistry with a precision that had never been possible before. And what the spectra revealed was a complexity that no one had quite anticipated. In the Chamaeleon cloud, another star-forming region that Webb observed in detail, the telescope found ices everywhere, not just in the densest cores where stars were actively forming, but throughout the cloud, even in regions that seemed relatively diffuse, relatively warm, relatively far from any obvious collapse. The ices were layered on the dust grains in ways that suggested a long and complicated history, with different molecules freezing out at different times, at different temperatures in different parts of the cloud. More strikingly, the telescope found complex organic molecules in these ices, molecules that, according to the old models, should not have been able to form until much later, until the cloud had collapsed, until a disk had formed around a young star, until the temperatures and densities had risen high enough for chemistry to really get going. But there they were, already present, already frozen onto the grains, already waiting to be incorporated into whatever planetary system eventually formed. The implication was profound. The chemistry of planet formation, the raw materials from which worlds are built, was not something that happened after a star was born. It was something that happened before, in the cold and the dark, in the patient molecular clouds where the dust drifted and the ices accumulated over millions of years. By the time a star finally ignited, the ingredients for planets, for oceans, perhaps even for life, were already in place. The third surprise was the disks. We have known for decades that young stars are surrounded by disks of gas and dust, the protoplanetary disks from which planets are thought to form. We have imaged these disks around hundreds of young stars, watched them evolve over millions of years, seen the gaps and rings and spirals that suggest planets are already carving out their orbits. But all of those observations were of relatively mature systems, disks that had already been around for 1 million years or more, disks where the dust had settled and the structure had stabilized and the earliest, most chaotic stages were long past. What Webb revealed was something earlier, something messier, something that challenged the neat, orderly picture of disk formation that the textbooks had described. In the Serpens cloud, the telescope imaged disks around protostars so young that they were still deeply embedded in the surrounding envelope of gas, still actively accreting material from the cloud, still years away from clearing out the dust and becoming visible in optical light. These were not the smooth, symmetric structures we'd seen around older stars. They were irregular, asymmetric, sometimes lopsided, shapes that spoke of ongoing collapse, of material still falling in from multiple directions, of a system that had not yet decided what it was going to become. And in some cases, the disks showed signs of structure that should not have been there yet. Rings, gaps, concentrations of dust at certain radii, as if something was already stirring the disk, already beginning to sweep up material, already forming, even at this impossibly early stage, the seeds of planets. This was not supposed to happen so fast. The old models had suggested that planet formation was a slow process, something that took millions of years after the disk had formed, after the star had ignited, after the system had settled into a stable configuration. But here were disks around protostars that were perhaps only a few 100,000 years old, already showing the telltale signs of planetary assembly. The planets, it seemed, were not waiting for the star to finish forming. They were forming alongside it, in the same chaotic, simultaneous tumult, as if star and planets were not separate stages of a sequential process, but different faces of a single entangled event. The Serpens cloud is not unique. In region after region, the telescope has found the same patterns: jets erupting from the youngest protostars, complex ices present before collapse has even fully begun, disks showing planetary signatures at ages that should be impossibly young, the Chamaeleon cloud, the Rho Ophiuchi complex, the Taurus molecular cloud. Everywhere Webb looks, it finds a version of star formation that is messier, faster, more chemically rich, and more simultaneous than the old models ever predicted. And this is where the story becomes, in a quiet way, unsettling. For decades, we built our understanding of how stars and planets form on a foundation of observations that could only show us the later stages, the survivors, the systems that had already emerged from their cocoons. We filled in the gaps with theory, with simulations, with educated guesses about what must be happening in the darkness. And those guesses were reasonable. They were consistent with the physics we understood. They produced models that seemed to match the observations we had. But they were wrong. Not completely wrong. The broad outlines of the story are still recognizable, still true. Gas collapses, stars ignite, disks form, planets coalesce. The sequence is real, but the details, the timing, the chemistry, all of that turns out to be more complicated than we imagined. The process is not as orderly as we thought. The stages are not as distinct. The boundaries between cloud and disk and planet are blurrier than the textbook suggested. What does it mean to have been wrong about something so fundamental? What does it mean to discover after decades of careful work that the story you have been telling is not quite the story that is actually unfolding? It means, in the gentlest possible way, that we are still learning, that the universe is still surprising us, that even the things we thought we understood, the birth of stars, the formation of worlds, the very processes that gave rise to our own sun and earth and the ground beneath your feet, are still revealing new facets, new complications, new beauties that we had not yet learned to see. Let us pause here for a moment and sit with what the telescope has shown us. In the Serpens cloud, about 1,000 light-years from where you are lying tonight, there is a protostar so young that it has not yet begun to shine. It is still wrapped in the dust and gas of its birth, still pulling material from the surrounding cloud, still growing, and from its poles, a pair of jets are streaming outward, narrow and bright in infrared light, carrying with them molecules that formed in the cold before the collapse, ices that will one day be incorporated into planets, organic compounds that might, in some distant future, become part of something alive. Around this protostar, a disk is already forming, not the smooth, settled disk of an older system, but a chaotic, irregular structure, still gathering itself, still deciding what shape it will take. And in that disk there are already hints of rings, of gaps, of concentrations of dust that suggest something is stirring, something is beginning to sweep up material, something that might in a few 100,000 years become a world. This is happening right now as you listen. The light that carries this story left the Serpens cloud about 1,000 years ago, give or take, which means that the images Webb captured show the system as it was around the time of the Norman conquest, around the time of the Song dynasty in China, around the time when the great cathedrals of Europe were just beginning to be built. The protostar in those images has continued to grow since then, has continued to pull in material, has continued to shape its disk and its jets and its eventual planetary system. By now it may be different, brighter, more stable, closer to igniting fusion, closer to becoming a true star. But we cannot know. The light from that change has not reached us yet. The story we see is always the story of the past, carried to us on waves that travel at the fastest speed the universe allows and still arrive too late to be called the present. This is one of the quiet truths of astronomy. We're always looking backward. The deeper we look, the farther back we see. The most distant galaxies Webb has imaged are not the galaxies as they are now, but as they were more than 13 billion years ago, when the universe itself was young, when the first stars were just beginning to ignite. when everything we know was still gathering itself out of the primordial dark. Even the sun, so close and so familiar, is 8 minutes in the past. The light that warms your face left its surface a little while ago, and you are always, in a small way, experiencing a star that no longer quite exists. But there is something comforting in this too. The universe is so vast and the speed of light so finite that we are surrounded at all times by a kind of cosmic memory, layer upon layer of the past preserved in the light that is still travelling toward us, waiting to be seen. The Serpens cloud as it was 1,000 years ago, the Andromeda galaxy as it was 2.5 million years ago, the cosmic microwave background as it was nearly 14 billion years ago, the oldest light we can ever hope to see. We are living in a universe that remembers itself, that carries its history written in photons, that offers up its past to anyone patient enough to look. The Chamaeleon Eye cloud is closer than the Serpens, about 500 light-years away in the southern sky, in a region of the Milky Way that is relatively sparse and quiet. It is named for the constellation Chamaeleon, the chameleon, a small and faint grouping of stars that was catalogued by European sailors in the 16th century when they first ventured far enough south to see constellations that had never been named by the astronomers of Greece and Rome and Arabia. The cloud itself is not visible to the naked eye, of course. Like all molecular clouds, it is dark, a region where the dust is thick enough to block the light of the stars behind it, where the temperatures are cold enough for molecules to survive, where the conditions are just right for the slow, patient work of star formation to begin. But in infrared light, the cloud reveals itself as a complex filamentary structure, threaded with streams and knots and dense cores where new stars are beginning to take shape. Webb observed this cloud in 2023 as part of a survey designed to study the ices in star-forming regions. The telescope's spectrographs were pointed at dozens of points within the cloud, measuring the absorption of background starlight, mapping the distribution of frozen molecules on the dust grains. And what the spectra revealed was a chemical richness that exceeded anything the astronomers had expected. Water ice was everywhere, as anticipated. Carbon dioxide too, and carbon monoxide and methane, all the simple molecules that form easily in the cold, that freeze out onto grains at the temperatures found deep within the cloud. But there were also more complex species: methanol, formaldehyde, formic acid, molecules with names like acetaldehyde and ethanol, organic compounds that contain carbon and hydrogen, and oxygen in configurations that hint at the chemistry of life. These molecules were not supposed to be there, or rather, they were supposed to be there, but in smaller quantities, in later stages, in the warm inner regions of protoplanetary disks, rather than the cold, outer reaches of the diffuse cloud. The old models had suggested that complex organic chemistry required energy: ultraviolet light from a young star, heat from accretion, the slow processing of simpler ices over millions of years. But here were complex molecules already in place, already frozen onto the grains before any star had formed, before any disk had emerged, before any of the processes that were supposed to drive complex chemistry had even begun. The implication was startling. The universe, it seemed, was better at chemistry than we had given it credit for. The raw materials for planets, for oceans, perhaps even for life, were being assembled in the cold and the dark, long before any star was there to warm them, long before any world was there to receive them. The molecular clouds were not just the birthplaces of stars. They were laboratories, factories, nurseries for the very molecules that would one day make up the surfaces of planets and the bodies of living things. And when those clouds finally collapsed, when stars finally ignited, when disks finally formed, the chemistry was already done. The ices were already in place. The complex organics were already waiting, frozen onto tiny grains of dust, ready to be delivered to whatever worlds eventually coalesced. There is a particular kind of wonder that comes from realizing how much has already happened before anything seems to begin. We tend to think of beginnings as clean: a starting gun, a first breath, a moment when something that did not exist suddenly does. But the birth of a star is not like that. It is more like the slow gathering of a river, the way 1,000 tiny streams come together over miles and years, each one adding its own water, its own sediment, its own history, until eventually there is a flow strong enough to carve canyons and carry ships. The protostars Webb has observed are not the beginning of the story. They are the middle, or perhaps not even the middle, just another chapter in a process that began millions of years earlier, when the molecular cloud itself first formed, when the dust first drifted together out of the diffuse interstellar medium, when the first molecules froze onto the first grains and the chemistry began. And before that, there was the dust itself, forged in the hearts of older stars, in the explosions of supernovae, in the slow winds of dying giants. Carbon and oxygen and silicon and iron, cooked in stellar furnaces over billions of years, scattered into space, gathered again by gravity, processed again by chemistry, until finally they found themselves in a cold cloud in the Serpens or the Chamaeleon, waiting to become part of something new. This is the great recycling of the cosmos. Nothing is wasted. Nothing is lost. The atoms in your body pass through the cores of stars, through the cold of molecular clouds, through the chaos of collapsing disks and forming planets, before they finally came together in the particular configuration that is you. And one day, not for a very long time, but one day, they will be scattered again to become part of something else, some other story, some other gathering of matter and energy and time. The telescope cannot show us all of this. Its instruments are exquisite, but they are not infinite. It can see the ices on the dust grains, the jets from the protostars, the rings in the young disks, but it cannot see the billions of years of stellar evolution that produced the dust, or the billions of years of cosmic history that produced the stars. It can only show us a moment, a long moment, stretched across light years and millennia, but still just a moment in the vast unfolding of the universe. And yet, even in that moment, there is enough wonder to fill a lifetime. Even in that single snapshot, there is enough complexity, enough beauty, enough surprise to keep us asking questions for generations. The Rho Ophiuchi cloud complex is one of the closest star-forming regions to Earth, about 400 light-years away, in the direction of the constellations Ophiuchus and Scorpius. It is a favourite target for astronomers because its proximity allows us to see details that would be blurred or invisible in more distant clouds, and it was one of the first regions Webb observed after it began science operations, a kind of proof of concept for the telescope's ability to peer through dust and reveal the hidden stages of star formation. The images Webb returned were breathtaking. They showed a landscape of gas and dust sculpted by the winds and radiation of young stars, a region where dozens of protostars were forming simultaneously, each one at a different stage of development, each one surrounded by its own envelope of material, its own jets, its own nascent disk. The colours in the images, false colours of course, representing different wavelengths of infrared light, painted a picture of a violent, active environment where the births of stars were not quiet or gentle but explosive, energetic, chaotic. And yet, for all the violence, there was also a strange kind of order. The jets, as chaotic as they seemed, were aligned, not randomly scattered, but pointing in roughly the same direction, as if the magnetic field threading through the cloud had imposed a kind of coherence on the chaos. The disks, as irregular as they were, showed the same rings and gaps that had been seen in older systems, as if some universal process was already at work, shaping the material, preparing it for planet formation. This is one of the deepest mysteries of star and planet formation, how order emerges from chaos. The initial conditions are messy: turbulent clouds, tangled magnetic fields, random motions, clumps and filaments and eddies that seem to follow no pattern, and yet somehow out of all that mess come stars and planets with predictable structures, with orbits and compositions and histories that can be understood, that obey the same laws of physics everywhere in the universe. Webb is not going to solve this mystery on its own. The telescope is an observer, not a theorist. It can show us what is happening, but not why. The explanation will have to come from the patient work of modelers and simulators, from the theorists who take the observations and try to build a framework that makes sense of them, who adjust their equations and run their codes and slowly, over years and decades, converge on a picture that matches what the telescope has revealed. But for now, the observations are enough. For now, it is enough to sit with the wonder of what we are seeing, the jets and the ices and the disks, the complexity and the simultaneity and the strangeness, and to recognise that we are living through a moment of discovery, a moment when the story of how stars and planets are born is being rewritten in real time, with every image the telescope sends back. There is a particular passage in the data from the Chamaeleon wide cloud that has stayed with me since I first learned about it. The spectrographs had been pointed at a dense core within the cloud, a region where the dust was thick enough to completely block the light of any stars behind it, where the temperatures had dropped to just a few tens of degrees above absolute zero, where the conditions were exactly right for a new star to begin forming. And in the spectrum of that core, the astronomers found something unexpected, a signature of carbon dioxide ice that did not match any of the laboratory measurements they had on file. At first, they thought it might be an error, an artifact of the data processing, a glitch in the instrument, something that would go away when they looked more closely. But it did not go away. The signature was real. The carbon dioxide ice in that core was in a form that had never been seen before, mixed with other molecules in a way that suggested a history of processing, of heating and cooling, of chemical reactions that had taken place over millions of years in the cold and the dark. What this meant, the astronomers realised, was that the ices in molecular clouds are not static. They are not simply frozen out of the gas and left unchanged for millions of years, waiting passively to be incorporated into planetary systems. They are active, they are evolving, they are undergoing chemistry even at temperatures close to absolute zero, even in the absence of light, even in conditions that should, by any reasonable accounting, be too cold for anything interesting to happen. The universe, it turns out, is more patient than we are. It is willing to let reactions proceed over timescales that we can barely imagine. Millions of years, tens of millions, hundreds of millions, until even the slowest chemistry has had time to run. And the products of that slow chemistry, the complex ices that Webb is now detecting, are the inheritance that every forming planetary system receives from the cloud that gave it birth. This changes things. If the chemistry is already done by the time a disk forms, then the composition of a planet is not determined by what happens in the disk, but by what happened in the cloud, millions of years before the star even existed. The ingredients are inherited, the recipe is set, and the variations we see between different planetary systems, why some have water and some do not, why some have organic molecules and some do not, why some give rise to life and some remain barren, may have less to do with the local conditions around each star than with the distant, ancient history of the molecular cloud from which everything emerged. And so, we arrive at a question that the telescope cannot answer, but that it invites us to ask. If the old models were wrong, if the chemistry happens earlier than we thought, if the disks show planetary signatures sooner than we expected, if the neat sequence of cloud, star, disk, planet is really a tangled, simultaneous mess, what else might we be wrong about? This is not a frightening question. It is, in a strange way, a hopeful one. It means that there is more to learn. It means that the universe still has secrets to reveal. It means that the next generation of telescopes, the next generation of observations, the next generation of patient, curious scientists will have something to discover. That the story is not finished, that the ending is not written, that we're still at the beginning of understanding how worlds are made. The James Webb Space Telescope is a remarkable instrument, but it is not the last word. It is, if anything, the opening of a door, a glimpse into a room we had only ever imagined, an invitation to step inside and look around and realize how much we still do not know. The observations it has made in the Serpens and the Chamaeleon and the Rho Ophiuchi are not conclusions. They are questions, posed in infrared light, waiting for answers that may take decades to arrive. And in the meantime, the clouds are still there, the protostars are still forming, the jets are still streaming out into the dark, the ices are still accumulating on the grains, the disks are still gathering, still shaping themselves, still preparing to become the birthplaces of worlds that will exist long after everyone alive today has returned to dust. It is all happening right now, as you listen. 1,000 light years away, and 400 and 500, in clouds with names like poetry, in the cold and the dark and the silence, the next generation of stars is being born. And you are part of that story, whether you know it or not. The atoms in your body, the ones that make up your hands and your heart and the soft tissue of your eyes that would be reading these words if they were written on a page, those atoms were forged in stars that died before the Earth existed. But more than that, the particular arrangement of those atoms, the way they came together to form water and carbon dioxide and amino acids, and all the intricate molecules that life requires, that arrangement was not invented here. It was inherited. It was passed down from a molecular cloud that collapsed more than 4.5 billion years ago, a cloud that had its own history, its own chemistry, its own slow, patient accumulation of complex ices on the surfaces of grains no larger than smoke particles. You are made of inherited ingredients. The recipe for you was written in the dark, in the cold, in the silence, long before there was a sun to warm you, or a planet to hold you, or a species to name you. This is what Webb is showing us in its patient infrared gaze. Not just that star formation is complicated, not just that the old models need revision, but that we are connected to these distant clouds in ways that are far more intimate than we ever imagined. The Serpens cloud is not just a laboratory for studying how stars form, it is a laboratory for studying how we formed. The chemistry happening there right now, the ices accumulating on those grains, the complex organic molecules assembling themselves in the cold, that is the same process that once made the raw materials for life on Earth. We are watching our own origin story unfold, 400 light-years away, delayed by the time it takes light to cross the gulf between us, but otherwise identical in every meaningful sense to the process that gave rise to everything we know. And this brings us to one of the quietest, most profound implications of what the telescope has found. If the chemistry of life begins in the cloud, not in the disk, not on the planet, then life itself may be far older than we thought. Not in the sense that there were organisms floating in space before the Earth formed, but in the sense that the preconditions for life, the molecular building blocks, the complex organic chemistry that living things require, these may be standard features of star formation. They may be built into the process. They may be as inevitable as the fusion of hydrogen into helium in a stellar core, as natural as the formation of a disk around a young star, as ordinary as the collapse of a cloud under its own weight. Life may not be a rare accident that happens only under special conditions. It may be a common inheritance, passed down from cloud to disk to planet, in an unbroken chain that stretches back billions of years. Consider for a moment what this means. Every star that forms in a molecular cloud receives a dowry of complex ices. Every disk that gathers around a young protostar inherits a library of organic molecules. Every planet that accretes from that disk carries in its bulk the chemical legacy of the cloud that made its star. And if that is true, if the ingredients for life are standard rather than exceptional, then the universe may be filled with worlds that have the raw materials for life, waiting for the right conditions to assemble themselves into something that breathes and grows and wonders about its own existence. This is not a proven fact. It is a possibility, an implication, a quiet suggestion that emerges from the data when you let yourself follow the chain of reasoning to its end. Webb has not discovered life. It has not even discovered the conditions for life. It has simply shown us that the chemistry we thought was rare may be common, that the molecules we thought were special may be ordinary, that the story of how life begins may need to be rewritten to include chapters that happen before planets even exist. Spare a thought too for the astronomers who are grappling with these implications. They are careful people, trained to be skeptical, trained to question their own conclusions, trained to look for alternative explanations before accepting the most dramatic interpretation. They are not rushing to declare that life is common in the universe. They are not making claims that the data cannot support, but they are also not ignoring what the data seems to be telling them. And what the data seems to be telling them is that the universe is more chemically rich, more molecularly complex, more ready for life than the old models ever suggested. The observations of the Serpens cloud in particular have been striking in this regard. The ices detected there are not simple. They are not just water and carbon dioxide, though those are present in abundance. They include carbon monoxide, which is expected, but also methanol and ammonia, and compounds that suggest even more complex organic chemistry is taking place. Methanol in particular is significant. It is a stepping stone, a precursor, a molecular building block that can lead to amino acids and sugars and other molecules that are essential for life as we know it. Finding it in the ices of a molecular cloud, before any star has formed, before any disk has gathered, before any planet has accreted, suggests that the assembly of life's raw materials begins earlier than anyone had imagined. And the Chamaeleon observations tell a similar story. The cloud is different from Serpens, smaller, quieter, less active in its star formation, but the ices are there, the complex molecules are there, the chemistry is proceeding in the same patient way. This is important because it suggests that the process is not unique to one cloud, not dependent on special conditions that happen to exist in Serpens but not elsewhere. It is general, it is widespread, it is perhaps universal. Return with me, one more time, to the question of timing, because this is where the implications become most profound. The old models assumed that the chemistry of life happened late in the process of planetary formation. A planet would form from the disk, would cool, would develop an atmosphere, would receive water and organic molecules from comets and asteroids, and would then, over hundreds of millions of years, develop the conditions necessary for life to emerge. The chemistry happened on the planet, in the oceans, in the shallow pools, in the hydrothermal vents. It was a planetary process, local and contingent and dependent on the particular history of each individual world. But if the chemistry begins in the cloud, then the timing changes dramatically. The molecules are already there, already assembled, already waiting before the planet even exists. The planet does not have to invent its chemistry from scratch. It inherits it. It receives it as a gift from the cloud that made its star, a dowry of complex ices that were assembled over millions of years in the cold and the dark and the silence. And if that is true, then the time required for life to emerge on a planet may be much shorter than we thought. The ingredients are pre-made, the assembly is partly done. All that remains is for the planet to provide the right conditions: liquid water, energy, stability, and the chemistry can proceed from where the cloud left off. This is speculation, of course. The telescope has not proven any of this. It has simply provided data that is consistent with this interpretation, data that invites us to consider possibilities that the old models did not allow. But it is speculation grounded in observation, speculation that emerges naturally from what we're seeing in the infrared light of these distant clouds. And it is speculation that, if true, would change everything we think we know about how life begins and how common it might be in the universe. It is worth pausing on the humility required to accept such a profound revision of our understanding. For decades, the models of star formation were elegant and satisfying. They told a clear story with a beginning, a middle, and an end. Cloud collapses, star ignites, disk forms, planets accrete, chemistry proceeds, life emerges. Each step followed naturally from the one before, and the whole process unfolded in a neat temporal sequence that made intuitive sense. The universe was orderly, the story was comprehensible, and we, the observers, could feel confident that we understood how the cosmos worked. But the universe does not owe us comprehensibility. It does not arrange itself for our convenience. It simply is what it is, and our job, as curious creatures who have developed the technology to look beyond our own small world, is to observe it honestly and revise our understanding when the observations demand it. This is what science does. This is what science has always done. And this is what the James Webb Space Telescope is forcing us to do now, with its patient, persistent gaze into the hearts of molecular clouds. Picture, if you can, the team of researchers who first analysed the data from the Serpens observations. They were looking at spectra, graphs of light intensity at different wavelengths, each peak and trough representing the absorption signature of a different molecule. They expected to see water ice. They expected to see carbon dioxide. They expected to see, perhaps, some carbon monoxide and a few other simple compounds. What they found was more complex than that. The spectra showed signatures of molecules that should not have been there in such abundance. Signatures that suggested chemical reactions were proceeding in ways that the models did not predict. There must have been a moment in some office or laboratory or conference room when someone looked at the data and realized that it did not fit, that the neat story they had learned and taught and believed was not quite right, that the universe was doing something unexpected, something surprising, something that required not just a tweak to the models but a fundamental rethinking of how star formation works. That moment, that quiet recognition that everything you thought you knew needs to be reconsidered, is one of the most precious experiences a scientist can have. It is the moment when the universe reveals itself to be stranger and more wonderful than you imagined, and we cannot leave this story without acknowledging the instrument that made these discoveries possible. The James Webb Space Telescope is a masterpiece of engineering, a collaboration among thousands of scientists and engineers working over decades to build something that had never been built before. Its primary mirror, more than 6 meters across, is composed of 18 hexagonal segments that unfold like a flower after launch, each one precisely aligned to within fractions of a wavelength of light. Its sun shield, the size of a tennis court, blocks the heat of the sun so that the telescope's instruments can cool to temperatures just a few degrees above absolute zero. cold enough to detect the faint infrared glow of objects that are themselves barely warmer than empty space. The telescope orbits at a point called the second Lagrange point, about 1 million miles from Earth, where the gravitational pulls of the Earth and the Sun balance in a way that allows it to stay in a stable position relative to both. From there, it looks outward into the universe, gathering light that has travelled for billions of years, revealing galaxies that formed when the universe was young, stars that are still in the process of being born, planets that are orbiting distant suns. It is the most powerful space telescope ever built, and it is showing us things that no previous instrument could see. But for all its power, for all its precision, for all its decades of development and billions of dollars of investment, the telescope is, in the end, just a tool. It is a way of seeing, a window onto the cosmos, an extension of our eyes and our curiosity into realms that we could never visit in person. What it reveals is not a product of the telescope itself, but of the universe it observes. The ices in the Serpens cloud were there before Webb looked at them. The protostellar jets were streaming before the first spectrum was captured. The complex chemistry of molecular clouds was proceeding for millions of years before human beings developed the technology to detect it. The telescope has not changed the universe. It has simply allowed us to see it more clearly. And this, perhaps, is the most humbling lesson of all. The cosmos does not need us. It does not require our understanding. It does not pause to wait for our instruments to catch up with its complexity. It simply continues, patient and vast and indifferent to whether we ever figure out how it works. The molecular clouds go on forming stars, the protostars go on igniting, the disks go on gathering, the ices go on accumulating, the chemistry goes on proceeding, and somewhere, in some cloud we have not yet observed, in some disk we have not yet imaged, in some planetary system we have not yet discovered, the conditions for life may be coming together right now, as you listen, as you breathe, as you drift towards sleep. Let us sit for a long moment with the scale of what we are discussing. A molecular cloud is not a small thing. The Serpens cloud complex spans dozens of light years. The Chamaeleon clouds, taken together, cover an area of the sky larger than your outstretched hand would cover if you held it up against the night. These are vast structures, containing enough gas and dust to form thousands of stars, enough raw material to build countless planetary systems, enough complex chemistry to seed billions of potential worlds with the ingredients for life, and they are just two examples among many. The Milky Way is filled with such clouds. Other galaxies are filled with similar structures. The universe in its entirety contains more molecular clouds than we could ever count, more protostars than we could ever observe, more disks and planets and potential homes for life than we could ever imagine. This is not a frightening vastness. It is a comforting one. It means that we are not alone in our existence, even if we are alone in our particular form. It means that the process that made us is not unique, not special, not a one-time accident that could never happen again. It means that the universe is, in some deep sense, on the side of complexity, on the side of chemistry, on the side of the slow patient accumulation of interesting molecules in interesting arrangements. We are part of a larger story, a cosmic narrative that began long before our sun formed and will continue long after our species has returned to dust. There is one more thing worth understanding about these observations, and it concerns the nature of light itself. The infrared light that Webb detects has travelled across space for centuries before reaching the telescope's mirrors. The photons that reveal the ices in the Serpens cloud left that cloud more than 400 years ago, when Galileo was first turning his telescope toward the sky, and Shakespeare was writing his final plays. The photons from the Chamaeleon clouds are similarly ancient, carrying information about conditions that existed generations before anyone alive today was born. This means that we are always looking into the past when we look at the stars. We are always seeing things as they were, not as they are. The protostars we observe forming may already have ignited. The disks we image may already have given birth to planets. The jets we watch streaming through the clouds may already have faded, their work done, their stars settled into the long, quiet burn of the main sequence. We do not know. We cannot know. The information travels at the speed of light, and there is no way to receive it faster. And yet, this does not diminish the significance of what we see. The past is not less real for being past. The chemistry that happened 400 years ago in the Serpens cloud is still relevant, still meaningful, still connected to the chemistry that is happening now, the universe does not forget. The complex ices that formed on those distant grains are still there, still accumulating, still waiting to be incorporated into planetary systems that may already exist or may still be forming. The story continues whether we watch it or not. It is worth trying just once to feel the strangeness of this. You are here on a small planet in a quiet corner of a galaxy that contains hundreds of billions of stars. You are made of atoms that were forged in the hearts of stars that died before the Earth existed. You carry in your body water molecules that may have been assembled on the surface of interstellar grains in a molecular cloud that collapsed to form the Sun. You are, in a very real sense, a product of the same processes that Webb is now observing in the Serpens and the Chamaeleon. You are the result of star formation. You are the inheritor of complex ices. You are what happens when the chemistry of a molecular cloud is given billions of years to develop on a rocky planet with liquid water and a stable climate. And this connection, this deep link between your body and the distant clouds, is not a metaphor. It is not a poetic fancy. It is a physical fact, grounded in the data, supported by the observations, consistent with everything we know about how the universe works. The same carbon that forms the backbone of your DNA was once locked in carbon dioxide ice on a grain in a cloud. The same oxygen that fills your lungs was once part of a water molecule frozen onto a silicate speck in the dark. The same nitrogen that forms the basis of your genetic code was once ammonia ice, accumulating slowly over millions of years in the cold of interstellar space. And somewhere, in a molecular cloud that may not even exist yet, the same processes are underway right now, building the raw materials for planets and oceans and perhaps, eventually, for life that will look back and wonder where it came from. This is the gift that the James Webb Space Telescope has given us. Not just images, though the images are beautiful, not just data, though the data is invaluable, but perspective, a way of seeing ourselves in the context of cosmic time, cosmic chemistry, cosmic processes that dwarf our individual lives while also making them possible. We are small, yes, we are brief, but we are not separate. We are woven into the fabric of the universe at the molecular level, connected to distant clouds and ancient ices by bonds that nothing can break. Consider, for a moment, the ice that contains sulfur dioxide. This is not a molecule that most people think about in their daily lives. It smells faintly of burnt matches when it sublimates, and it forms in tiny quantities on the surfaces of grains in the coldest regions of the clouds. But Webb has detected it, mapped its distribution, measured its abundance in ways that were never possible before, and what the measurements show is that sulfur dioxide ice is more common than the old models predicted, more widespread, more deeply embedded in the chemistry of star-forming regions than anyone had expected. This matters because sulfur is one of the elements essential for life as we know it. It forms part of certain amino acids, the building blocks of proteins. It participates in reactions that drive the metabolism of cells. Without sulfur, life on Earth would be impossible, or at the very least profoundly different. And yet we had always assumed that sulfur was relatively rare in the early stages of planet formation, that it was locked away in forms that would not easily participate in the chemistry of young worlds. The Webb observations suggest otherwise. They show sulfur dioxide ice mixed with water ice, with carbon dioxide ice, with methanol and ammonia and all the other molecular species that make up the frozen mantles of interstellar grains. They show sulfur participating in the chemistry from the very beginning, available and ready to be incorporated into the planets that will eventually form. This is a small revision to our understanding perhaps, but it is a meaningful one. It means that the inventory of elements available for building life may be richer than we thought, more complete, more ready to support the emergence of complex chemistry. Spare a thought too for the astronomers who spend their careers studying these observations. They work in offices that look much like any other, with computers and coffee cups and family photographs on their desks. They attend meetings and write grant proposals and worry about deadlines. But their work connects them to processes that operate on scales of space and time that the human mind can barely grasp. They spend their days thinking about the chemistry of clouds that are measured in light years, about grains that are measured in microns, about temperatures that would freeze any substance on Earth into brittle solidity. They translate the faint light of distant nebulae into numbers, and those numbers into understanding, and that understanding into stories that connect us all to the cosmos. It is quiet work mostly. It does not make headlines. The papers they publish are read by hundreds of other specialists, not millions of curious readers. But it is essential work, patient work, the slow accumulation of knowledge that eventually transforms how we understand our place in the universe. Every spectrum analysed, every ice feature identified, every protostar classified adds another piece to a puzzle that humanity has been assembling since the first people looked up at the stars and wondered what they were. Return with me, one more time, to the images themselves. If you could see what Webb sees, if you could perceive the infrared light that your eyes cannot detect, the molecular clouds would look nothing like the dark patches you see in visible light photographs. They would glow. They would shimmer with the light of embedded stars, with the warmth of collapsing cores, with the radiance of shocked gas where jets slam into the surrounding medium. They would be alive with colour, with structure, with detail that reveals the fingerprints of physics and chemistry at work. The Serpens cloud in particular shows features that earlier telescopes could only hint at. There are filaments of denser gas threading through the cloud like veins in a leaf, channels along which material flows toward the forming stars. There are cavities carved by outflows, bubbles of cleared space where the jets have pushed the surrounding gas aside. There are bright knots where the jets encounter particularly dense clumps of material and pile up into hot, glowing shockwaves. And everywhere, there are the signatures of ices, of complex chemistry, of molecules that have been building toward something for millions of years. The Chamaeleon clouds show different features, reflecting their different evolutionary state. These clouds are quieter, calmer, more quiescent. The star formation happening within them is less vigorous, less dramatic, more like a slow simmer than a rolling boil. But this makes them ideal for studying the very earliest stages of the process, before the protostars grow powerful enough to disrupt their surroundings with outflows and radiation. In the Chamaeleon, Webb can see the pristine conditions that exist before star formation really gets underway, the baseline chemistry that represents the starting point for everything that follows. And what Webb sees in the Chamaeleon is ice, vast amounts of ice, coating every grain, filling the cloud with frozen molecules that will eventually become part of planetary systems. The ice is so abundant that it dominates the infrared spectra, overwhelming the signals from the underlying silicate grains with a forest of absorption features that reveal molecule after molecule. Water ice, carbon dioxide ice, carbon monoxide ice, methane ice, ammonia ice, methanol ice, and more, all mixed together in proportions that tell the story of how they formed and how they have been processed by the radiation environment of the cloud. Picture, if you can, the scale of this chemistry. The Chamaeleon clouds contain enough water ice to fill the Earth's oceans millions of times over. They contain enough carbon dioxide ice to give atmospheres to billions of worlds. They contain enough methanol to fuel civilizations, enough ammonia to fertilize planets, enough methane to heat homes on worlds that do not yet exist. All of it is there, frozen, waiting, accumulating slowly over timescales that make human history seem like the blink of an eye. And this chemistry is not static. Even in the cold, even in the dark, reactions continue. Cosmic rays penetrate the clouds and break apart molecules, creating fragments that recombine in new ways. Ultraviolet light from distant stars seeps into the outer layers of the clouds and drives photochemistry on the surfaces of grains. Atoms and molecules migrate slowly across the icy surfaces, finding each other, bonding, building structures that grow more complex with time. The clouds are laboratories, vast cosmic laboratories where experiments in chemistry run continuously for millions of years. Let us sit for a long moment with the implications of this continuous chemistry. It means that the composition of the ices changes over time, evolving toward greater complexity. It means that the longer a cloud persists before collapsing, the more elaborate its chemistry becomes. It means that the planets that eventually form inherit not just the raw materials but also the processing, the molecular diversity, the chemical head start that the cloud has accumulated. Some clouds collapse relatively quickly, within a few million years of their formation. Others persist for tens of millions of years, slowly accumulating complexity while they wait for the right gravitational perturbation to trigger their collapse. The planets that form from these longer-lived clouds may inherit a richer chemical legacy, more complex molecules, more building blocks for the emergence of life. Or they may inherit chemistry that has been processed too much, molecules that have been broken down and rebuilt so many times that they have lost their original utility. We do not know yet which scenario is more favourable for the emergence of life. We do not know whether the fastest or the slowest clouds produce the most promising planets. But Webb is giving us the tools to start answering these questions, to start mapping the relationship between cloud lifetime and chemical complexity, to start understanding how the timing of star formation affects the chemistry of planets. There is a smaller, quieter story woven through all of this, and it concerns the simple question of how we know what we know. The molecules in the ices do not announce themselves with name tags. They do not glow with labels identifying their composition. They reveal themselves through subtle changes in the way they absorb light, changes so small that they can only be detected with the most sensitive instruments, analysed with the most sophisticated techniques. The astronomers who study ices have spent decades learning to read these subtle signals, to distinguish the fingerprint of water ice from the fingerprint of carbon dioxide ice, to tease apart the overlapping features of molecules mixed together on the same grain. This work began long before Webb launched. It began in laboratories on Earth, where scientists synthesized ices under conditions designed to mimic those in interstellar space. They cooled chambers to When Webb observes an ice feature in the Serpens cloud, the spectrum can be compared to the laboratory references, and the molecules can be identified. Worth pausing on the nature of this collaboration. The astronomers who interpret Webb's spectra rely on chemists who may have retired or died before the telescope even launched. The laboratory work done in the 1980s and 1990s is being used today to analyse data from an observatory that did not exist in anyone's imagination when that work began. Knowledge transcends the individual lifetimes of those who create it. It passes from generation to generation, accumulating, growing, becoming more complete and more reliable with each passing decade. This is one of the quiet miracles of science. The woman who measured the infrared spectrum of methanol ice in a cold chamber in 1987 could not have known that her measurements would be essential for understanding observations made by a telescope launched in 2021. She did the work because it was interesting, because she wanted to understand, because the questions seemed worth answering. And now, long after she may have moved on to other work or other phases of her life, her contribution remains, embedded in the literature, available to anyone who needs it, a gift from the past to the future. And we cannot leave this story without considering the people who built the telescope itself. The James Webb Space Telescope is one of the most complex machines ever constructed by human beings. It required 25 years of development, the collaboration of thousands of engineers and scientists, the solution of problems that had never been faced before. The primary mirror, made of 18 hexagonal segments coated with gold, had to be designed to unfold in space and align itself with an accuracy measured in nanometers. The sun shield, made of 5 thin layers of specialized material, had to deploy flawlessly after years of being folded up in the rocket fairing. The instruments had to be cooled to temperatures just a few degrees above absolute zero and kept there, continuously, for the duration of the mission. Any one of these requirements would have been challenging on its own. Together, they represented one of the greatest engineering challenges in the history of space exploration. There were moments when the project seemed impossible, when the budget overruns and schedule delays threatened to cancel it entirely. There were congressional hearings and independent reviews and public controversies about whether the telescope was worth the cost, worth the risk, worth the decades of waiting. And yet it flew. It deployed. It aligned. It cooled. It began returning images that exceeded even the most optimistic predictions. Every ice spectrum it records, every protostar it images, every jet it resolves is a testament to the thousands of people who refused to give up, who kept working through the setbacks and the doubts, who believed that the science was important enough to justify the effort. This too is part of the story that Webb tells us about ourselves. We are capable of sustained effort across decades. We can work together across national boundaries and institutional barriers toward goals that no single person or organization could achieve alone. We can create tools that reveal aspects of the universe that our unaided senses could never perceive. We can, when we choose to, be patient, collaborative, and visionary in ways that make transcendent discoveries possible. The ices in the Serpens cloud do not care who built the telescope or how long it took. They absorb infrared light according to the laws of physics, indifferent to human timelines and budgets. But we care. We should care. Because the ability to see those ices, to understand their composition, to trace their relationship to the chemistry of planets and the origin of life, is something that we made possible through our own efforts. It is a gift we gave ourselves, a tool for extending our understanding beyond the limits of our biology. And so the infrared light continues to arrive, photon by photon, carrying information from the past to the present, from the distant to the near, from the cold darkness of the clouds to the warm sensors of the telescope. The molecules continue to form on the surfaces of grains, building toward complexity, storing energy and structure in bonds that may someday contribute to the chemistry of a living world. The protostars continue to gather mass, the jets continue to clear their channels, the disks continue to organize themselves into patterns that will become planetary systems. It is all happening tonight, as you rest, as you breathe, as you drift towards sleep. Somewhere in the Serpens cloud, a grain of silicate is acquiring another layer of water ice. Somewhere in the Chamaeleon, a carbon dioxide molecule is forming from the collision of carbon monoxide and oxygen on a frozen surface. Somewhere in a protoplanetary disk we have not yet observed, the first pebbles are beginning to stick together, the first steps toward planethood being taken in silence and darkness. The universe does not wait for our attention. It does not pause while we sleep or pause while we wake. The chemistry proceeds, the physics unfolds, the story continues with or without our observation. But when we do observe, when we do pay attention, when we do train our telescopes on the distant clouds and decode the messages hidden in the light, we become part of the story in a new way. We become witnesses, chroniclers, inheritors of knowledge that connects us to processes far older and far larger than ourselves. And this is perhaps the most remarkable thing of all. Not that the universe creates stars and planets, though that is remarkable enough. Not that chemistry proceeds in the darkness between the stars, though that too fills us with wonder. But that we, ourselves products of this same chemistry, descendants of these same processes, have found ways to look back across the light years and understand what is happening. We are stardust contemplating stardust. We are the universe developing instruments to examine its own workings, asking questions about its own origins, piecing together the story of its own becoming. Consider for a moment what it means that the same carbon atoms now present in your body were once forged in the cores of stars that died before the sun was born. The oxygen you breathe was created in stellar furnaces and scattered into space by explosions that happened billions of years ago. The water in your cells contains hydrogen that has existed since the first few minutes after the Big Bang, hydrogen that has cycled through clouds and stars and planets and comets, that has been ice and vapor and liquid, that has participated in chemistry on the surfaces of grains in regions not unlike the ones Webb is observing now. You're made of the same materials that Webb sees assembling in those distant nurseries. You are what happens when this chemistry has enough time, enough stability, enough gentle warmth to organize itself into complexity, into metabolism, into thought, into the capacity to build telescopes and send them to the second Lagrange point and use them to study the very processes that made you possible. This connection is not metaphorical. It is not poetic license or inspirational exaggeration. It is the literal truth of your composition, verified by spectroscopy, confirmed by nuclear physics, as solid a fact as any we possess. The light that Webb collects from the Serpens cloud carries information about chemistry that is ancestrally related to your own chemistry. Not the same molecules, not the same particular atoms, but the same processes, the same reactions, the same cosmic recipe being followed in a kitchen that has been operating for billions of years. It is worth pausing on what the old models told us and why the new observations are so quietly revolutionary. For decades, the standard picture of star formation went something like this. A cloud of gas and dust, if it becomes dense enough and cold enough, can begin to collapse under its own gravity. The collapse is opposed by various pressures, by turbulence, by magnetic fields that thread through the cloud and resist being squeezed. But if the gravity wins, if the cloud can shed enough of its supporting forces, it will contract slowly at first, then faster, falling inward toward its own centre. As the material falls, it heats up, and eventually the centre becomes hot enough and dense enough to ignite nuclear fusion. A star is born. The leftover material around it settles into a disk, and from that disk, planets form. This picture was elegant. It was mathematically tractable. It made predictions that seemed to match the observations available at the time. But the observations available at the time were limited. Ground-based telescopes could see stars after they had formed, could study their properties and infer their histories, Space telescopes like Hubble could peer into some stellar nurseries and see shapes, outlines, the silhouettes of disks against bright backgrounds. The Spitzer Space Telescope, with its infrared eyes, could see deeper into the dusty regions, could detect warm objects embedded in clouds, could study some aspects of the chemistry. But none of these instruments could see what Webb can see. None of them had the sensitivity, the resolution, the wavelength coverage to probe the coldest, densest, most obscured regions where the crucial early stages of formation actually occur, and so the models were built on indirect evidence, on theoretical considerations, on the assumption that the parts of the process we could not observe behaved according to the principles we understood from the parts we could observe. This is how science often works, and it is not a failing. You build the best model you can with the data you have, and you make predictions, and you test those predictions when new data becomes available. The expectation was that Webb would confirm the models, would fill in details, would refine parameters. The expectation was not that Webb would show us a process fundamentally different from what we had imagined, but that is what has happened. Not all at once, not with a single dramatic discovery, but slowly, observation by observation, spectrum by spectrum, the picture has shifted. The timelines do not match, the chemistry does not match, the sequences do not match. What we are seeing in the Serpens cloud, in the Chamaeleon complex, in the other regions Webb has examined, does not fit neatly into the elegant progression the old models described. Spare a thought too for the scientists who built those models. They were not wrong in any simple sense. They were doing the best science possible with the information available to them. Many of them are still active researchers, now working with the Webb data, revising their models, adjusting their understanding. This is what good scientists do. They do not cling to their ideas when the evidence contradicts them. They update, they revise, they follow the data wherever it leads. And the data from Webb is leading somewhere unexpected. One of the first surprises came from the ices. The models predicted that ice would form on dust grains in a particular sequence, building up in layers like the rings of a tree, with the most volatile species on the outside and the more refractory species closer to the grain surface. Water ice would form first, because water is sticky and abundant, then carbon dioxide, then carbon monoxide, then perhaps methanol and other more complex molecules if the conditions were right. This layered structure was expected because it followed logically from the physics of adsorption and the temperatures at which different molecules would freeze out of the gas phase. But Webb sees something different. The ices are mixed in ways the models did not predict. Species that should be in separate layers are found together. The ratios of different molecules do not match the expectations. In some cases, molecules are present that should not be able to form under the conditions the models assumed. In other cases, molecules that should be abundant are strangely absent or depleted. The chemistry is more complicated, more dynamic, more surprising than the simple layered picture suggested. Return with me, one more time, to the surface of a single dust grain in the Serpens cloud. Picture it as it actually is, not as the models imagined it. The grain is not a passive substrate waiting for molecules to land like snow on a rooftop. It is an active participant in the chemistry, a catalyst, a scaffold, a substrate whose properties influence what reactions can occur. The surface is irregular, pocked with binding sites where molecules stick more or less strongly depending on the local geometry. The temperature is not uniform across the grain. There are warmer spots and colder spots, places where molecules can move and places where they are frozen in place. There are cosmic rays passing through occasionally, ionizing molecules, breaking bonds, creating reactive species that can combine in unexpected ways. The old models treated the grain surfaces as simple, uniform, predictable. The new observations suggest they are complex, variable, and full of surprises. This matters because the chemistry that happens on these surfaces is the chemistry that eventually contributes to planets. The molecules that form on dust grains are the molecules that get incorporated into planetesimals, the molecules that become part of asteroids and comets, the molecules that may someday rain down on a young planet and contribute to its oceans, its atmosphere, perhaps even its biology. If we misunderstand the chemistry on the grains, we misunderstand the starting conditions for planets. We misunderstand the inventory of materials from which worlds are built. There is one more thing worth understanding about how this revision is proceeding. It is not that the old models were completely wrong, it is that they were incomplete. They captured some aspects of the truth but missed others. They worked well enough for the observations available at the time, but they fail when confronted with the higher resolution, deeper sensitivity, broader wavelength coverage that Webb provides. This is a common pattern in the history of science. Newtonian gravity was not wrong. It was incomplete, a limiting case of a deeper theory that Einstein would eventually provide. The same is true here. The old models of star formation are not being discarded entirely. They are being expanded, refined, complicated, made more accurate by incorporating the new information. And we cannot leave this story without acknowledging the human dimension of this revision. There are careers built on the old models, there are textbooks written, lectures delivered, students trained in a picture of star formation that is now being substantially revised. This is not comfortable for everyone. It requires intellectual flexibility, a willingness to hold one's ideas lightly, an acceptance that understanding is always provisional and subject to revision. The scientists involved are handling this with remarkable grace, for the most part. The excitement of the new discoveries outweighs the discomfort of the revision. The opportunity to see something genuinely new, to learn something genuinely surprising, is more valuable than the security of believing you already understood. Let us sit for a long moment with the question of timing. The old model suggested that star formation was relatively quick, at least on cosmic scales. A cloud would begin to collapse, and within a few 100,000 years, a star would be born. The process had distinct phases that followed one another in predictable sequence. First the collapse, then the protostar, then the T-Tauri phase, then the main sequence. Each phase had characteristic properties, characteristic signatures, characteristic timescales. But Webb is showing us systems that do not fit this tidy progression. Some protostars seem older than their surroundings suggest they should be. Some disks appear more evolved than the stars they orbit. Some jets persist longer than the models predicted, continuing to operate after the accretion that powers them should have diminished. The timing is off. The synchronization that the models assumed is not as tight as we thought. This matters because timing affects chemistry. If the protostar heats its surroundings faster than expected, the ices sublimate sooner, the chemistry shifts earlier, the inventory of molecules in the disk is different from what the models predicted. If the disk survives longer than expected, it has more time to process its materials, more time for chemistry to proceed, more opportunity for complex molecules to form. If the jet persists longer, it continues to inject energy into the surrounding cloud, stirring up the medium, preventing material from settling into the simple configurations the models assumed. Picture, if you can, a protoplanetary disk as Webb sees it. Not a smooth, featureless ring of gas and dust, but a complex structure with gaps and rings, with spiral arms and asymmetries, with variations in composition from one region to another. The old models assumed these structures formed late, after the disk had settled into a stable configuration. Webb shows us that they form early, that the disk is already structured when it is still young, that the processes that will eventually form planets are already at work when the star itself is still gathering mass. There is a smaller, quieter story woven through all of this, and it concerns the molecules that are not there. Webb's spectra can detect what is present in the clouds and disks, but they can also reveal what is absent. And some of the absences are surprising. Certain molecules that the models predicted should be abundant are found at much lower levels than expected. Others that should be rare are surprisingly common. The chemical inventory of these regions is not what we anticipated. One example involves ammonia, a molecule of nitrogen and hydrogen that is common in the outer solar system, and was expected to be abundant in protostellar environments. Webb finds it, but not always where the model said it should be, and not always in the quantities predicted. Another example involves sulfur-bearing molecules, which are depleted in the dense clouds by factors that are difficult to explain with standard chemistry. The sulfur should be there, but it is not, or rather it is present in forms we do not yet understand, hidden in species that do not show up clearly in the spectra. These absences are as informative as the presences. They tell us that the chemistry is more complex than we modelled, that there are pathways we did not consider, sinks we did not account for, processes we did not include in our calculations. Each unexplained absence is a puzzle, a clue, an invitation to revise our understanding. It is worth trying just once to feel the scale of what Webb is revealing. These observations are not just about distant clouds that have no connection to us. They're about the processes that created the solar system, that made the Earth possible, that provided the raw materials from which life emerged. When Webb studies a protoplanetary disk in the Chamaeleon complex, it is studying a system that is not unlike the infant solar system 4.5 billion years ago. The chemistry it observes, the structures it resolves, the dynamics it traces are windows into our own past, glimpses of what was happening when the sun was young and the planets were just beginning to form. The Chamaeleon complex is closer than the Serpens cloud, only about 500 light-years away, close enough that Webb can resolve individual young stellar objects with remarkable clarity. Here the telescope has found disks that are already showing signs of planet formation, gaps that may indicate the presence of unseen planets sweeping up material, structures that hint at the gravitational sculpting that will eventually produce planetary systems. And the ices in these disks are not uniformly distributed. Webb can see that the water ice is concentrated in certain regions, that the carbon dioxide is found elsewhere, that there are gradients and variations that the old models did not predict. The disk is not a well-mixed soup of ingredients. It is a structured environment where different materials are found in different places, where the starting conditions for planet formation vary from one region to another. This has implications for the diversity of planets. If the disk is heterogeneous, if different regions have different chemical compositions, then planets forming in different parts of the same disk might have very different initial inventories. A planet forming close to the star, where the temperatures are high and the ices have sublimated, would have a different composition from a planet forming farther out, where the ices are preserved. This could help explain why the solar system contains such a variety of worlds, from the rocky inner planets to the icy moons of the outer solar system, each with its own distinct composition and character. Consider for a moment the water in Earth's oceans. Where did it come from? This question has occupied planetary scientists for decades, and the answer is still not entirely settled. Some of the water may have been present from the beginning, incorporated into the Earth as it formed from the dusty disk around the young sun. Some may have been delivered later by comets and asteroids that crashed into the young planet and deposited their icy cargoes. The relative contributions of these sources are still debated, but Webb's observations of protoplanetary disks are providing new constraints on this question. By studying where the water ice is located in disks around other stars, by tracing how it moves and evolves as the disk ages, by understanding how it gets incorporated into the planetesimals that will eventually become planets, we can begin to build a more complete picture of how water gets distributed in forming planetary systems. This is not just abstract knowledge. This is the story of how our planet became habitable, how the oceans formed, how the conditions for life were established. The universe does not owe us explanations. It is under no obligation to be comprehensible, to match our expectations, to fit neatly into our models, and yet, remarkably, it does seem to be comprehensible, at least in part. The laws of physics apply everywhere we have looked. The chemistry that Webb observes in distant clouds is the same chemistry that operates in laboratories on Earth. The processes that formed other planetary systems are the same processes that formed ours. There is a unity to nature, a consistency that makes science possible, that allows us to learn about the distant by studying the near, about the past by observing the present, about the universal by examining the particular. This is a gift, not a gift from any giver, but a fortunate circumstance, a happy fact about the universe we find ourselves in. It could have been otherwise. The universe could have been arbitrary, chaotic, different from one place to another in ways that defied understanding. But it is not. It is lawful, patterned, consistent. And this consistency is what allows us to look at light from a molecular cloud 500 light-years away and learn something about the chemistry that contributed to our own existence. The night continues. The telescope continues its observations. The clouds continue their slow transformations. And somewhere, in a disk we may never observe directly, the first pebbles of a future planet are beginning to stick together. The first steps in a journey that will take millions of years and end with a world, perhaps a world with oceans, perhaps a world with life, perhaps a world with beings who will someday build their own telescopes and look back at the clouds where their atoms were assembled, wondering as we wonder, at the strange and beautiful chain of events that led from darkness and dust to warmth and thought, and the quiet miracle of being able to ask the question at all. And so, we return to the question of timing, which is threaded through everything we have seen tonight. The old models told us a story with clear stages, a sequence that proceeded in an orderly fashion from collapse to disk to planet. First, the cloud falls inward, then the disk forms, then the disk cools and settles, then the dust grains begin to grow. Then, after millions of years of patient accumulation, the first planetesimals emerge. It was a tidy narrative, and for decades it seemed to match what we observed. But Webb has been whispering something different. The timing is wrong. Not wrong in the sense that the stages do not occur, but wrong in the sense that they do not wait for each other. They overlap, they interleave, they run in parallel rather than in series. The chemistry of planet formation does not wait for the disk to finish forming. The first steps toward building a world begin while the cloud is still falling, while the envelope is still feeding the disk, while the young star is still gathering its mass. This is perhaps the most profound revision that the telescope has quietly introduced. It is not a dramatic overturning of everything we thought we knew. The basic physics remains sound. Gravity still pulls, angular momentum still flattens, dust still sticks. But the choreography is different from what we imagined. The dance begins earlier than we thought, and the dancers do not wait for their cues. Spare a thought for the theorists who must now revise their models. For years they built simulations that treated each phase as distinct. The collapse phase was one calculation, the disk phase was another, the planet formation phase was a third. Each had its own specialists, its own conferences, its own journals. The boundaries between them were not just computational conveniences, they reflected a belief about how nature actually organized itself. Now those boundaries are blurring. The observations demand models that track the chemistry from the cold cloud all the way through to the finished planet, without artificial breaks in between. The ices that form on dust grains in the dark cloud must be followed as those grains fall into the disk, as they drift inward or outward, as they are heated and cooled, as they collide and stick, as they are eventually incorporated into the cores of forming worlds. The thread cannot be cut. This is harder than it sounds. The physics at each stage is different. The temperatures span 4 orders of magnitude. The densities span even more. The timescales range from tens of thousands of years for the initial collapse to millions of years, for the disk evolution to hundreds of millions of years for the final assembly of terrestrial planets. No single simulation can capture all of this. The computational demands are beyond anything currently possible. And so, the theorists must find clever approximations, must decide which processes to include and which to simplify, must build models that are good enough to match the observations without being so complex that they cannot be run. It is painstaking work, unglamorous work, the kind of work that rarely makes headlines. But it is essential. Without theory, observations are just pictures. With theory, they become stories, narratives, explanations. The interplay between the two is the heartbeat of science, the back and forth that slowly, incrementally brings us closer to understanding. Return with me, one more time, to the Chamaeleon region. We have spoken of Chamaeleon, the active cloud with its embedded protostars and its rich chemistry. But there is another cloud nearby, Chamaeleon 2, smaller and quieter, with fewer young stars, less dramatic activity. For years it received less attention from observers. It seemed less interesting, less likely to reveal new secrets. But Webb found something there too. In the diffuse material between the denser cores, in the regions where no star is currently forming, the telescope detected ices. Not as abundant as in the dense cores, but present nonetheless. Carbon dioxide ice, water ice, fainter signatures of other species. The cloud is cold enough, even in these less dense regions, to allow ices to form on the surfaces of dust grains. This matters because it tells us that the chemical preparation for star formation begins before the collapse itself. The raw materials, the ices that will eventually become the stuff of planets, are already being assembled in the diffuse medium, waiting for gravity to gather them together. When a core finally does form, when the density increases and the collapse begins, it does not start with pristine, ice-free dust. It starts with dust that has already been processed, already been coated with frozen molecules, already been prepared for the chemistry to come. The clouds are not passive reservoirs of raw material, they are factories, slowly and quietly building the chemical inventory that will be passed down to the next generation of stars and planets. Every moment that a dust grain spends drifting through the cold depths, Every collision with a gas phase molecule that sticks to its surface and freezes adds to this inventory. The clouds remember. They accumulate. They prepare. And when the collapse comes, when gravity finally wins and the material begins to fall inward, it carries this memory with it. The ices are not formed anew in the disk. They are inherited from the cloud, modified along the way but fundamentally continuous with what came before. The chemistry of a planet is not decided at the moment of planet formation. It is decided earlier, in the cold and the dark, in the slow drift of grains through the void, in the patient accumulation of frozen molecules that will one day become oceans and atmospheres and perhaps, in some distant place we will never see, the building blocks of life. There is one more thing worth understanding about these observations, something that speaks to the nature of scientific discovery itself. Webb did not set out to overthrow the models of star formation. The telescope was not designed with revolution in mind. Its instruments were built to be sensitive and precise, to gather light with unprecedented efficiency, to see details that had never been seen before. The goal was simply to look more carefully, to observe more deeply, to push back the boundaries of what was visible. The revisions to our understanding emerged not from a dramatic experiment designed to test a specific hypothesis, but from the accumulated weight of many observations, each one adding a small piece to the puzzle, each one slightly shifting the picture. No single image overturned the old models, no single spectrum proved them wrong. Instead, the evidence accumulated quietly, persistently, until the totality of what was observed could no longer be accommodated within the old framework. This is how science usually works, though it is not how science is usually told. The stories we hear are stories of breakthrough moments, of eureka discoveries, of single observations that changed everything. And sometimes that does happen. But more often the changes come gradually, through the slow accretion of evidence, through the patient work of many observers over many years, through the steady refinement of instruments and techniques that allows us to see a little more clearly, a little more deeply, a little more truly. Webb is part of this tradition. It is not a revolutionary telescope in the sense of overturning everything that came before. It is an evolutionary telescope, building on what Spitzer and Herschel and ground-based observatories had accomplished, pushing further, seeing more. The infrared universe that it reveals is not a different universe from the one we knew. It is the same universe, seen more completely. The molecular clouds that Webb observes are the same clouds that astronomers have been studying for decades. But now we can see inside them, can trace the chemistry happening in their depths, can watch the earlier stages of star and planet formation unfold. Consider, for a moment, the engineers and scientists who built this telescope. Most of them will never become famous. Their names will not appear in textbooks. They will not receive the accolades that go to the theorists who propose new ideas or the observers who make dramatic discoveries. But without them, none of this would be possible. Every mirror segment, every detector, every cooling system, every piece of software that processes the data represents years of work by people who believed that seeing the universe more clearly was worth the effort. And now the telescope is out there, 1 million miles from Earth, faithfully gathering light night after night. It does not know what it is seeing. It does not understand the significance of its observations. It is just a machine, an extraordinarily sophisticated machine doing what it was designed to do. The understanding comes later, when the data arrives on Earth and human minds begin to make sense of it. The telescope sees, we understand. That partnership between machine and mind, between technology and thought, is what makes astronomy possible. Let us sit for a long moment with the question of what all of this means for our own origins. Every element heavier than hydrogen and helium in your body was forged inside a star. Every oxygen atom, every carbon atom, every nitrogen atom was created in the nuclear furnaces of stellar cores, released when those stars died, scattered into the interstellar medium, gathered into clouds, incorporated into new stars and the planets that formed around them. This is the cosmic recycling that makes complex chemistry possible, that makes planets possible, that makes life possible. But Webb is showing us that the story is more intricate than this simple recycling narrative suggests. It is not just about which elements are present. It is about how those elements are arranged, which molecules they form, where those molecules end up in the protoplanetary disk, how they are processed during the chaotic early history of the planetary system. The same elements, arranged differently, would produce a different kind of planet. The Earth is not just a random assortment of heavy elements. It has a specific composition, a specific ratio of rock to water, a specific inventory of volatile molecules. Why this particular composition rather than some other? Part of the answer lies in where the Earth formed in the solar system, how far from the Sun, what temperature it experienced as it grew. But part of the answer lies earlier, in the cloud, in the disk, in the chemistry that was already underway before the Sun even ignited. Webb cannot tell us directly about our own solar system. That history is 4.5 billion years gone. The cloud that birthed the Sun dispersed long ago, its material scattered across the galaxy, some of it eventually incorporated into other stars, other planets, other systems. We cannot go back and observe our own origins, but we can observe other systems at various stages of formation, can piece together a composite picture, can build a story from the fragments. This is what astronomers call comparative planetology, extended backward in time. By studying many disks at many ages around many different types of stars, we can begin to understand the range of outcomes that are possible, the factors that determine whether a system will produce rocky planets or gas giants or icy worlds, whether it will be hospitable to life or barren and empty. The universe provides the laboratory, we provide the questions. Picture, if you can, the scene unfolding right now in some molecular cloud we have yet to name. Somewhere in the galaxy, perhaps a few thousand light years away, perhaps much farther, a core is beginning to collapse. The dust grains are falling inward, carrying their coatings of ice. A disk is forming, thin at first, then thickening as more material arrives. Jets are beginning to punch through the surrounding envelope, clearing channels for material to escape. The first clumps of solid matter are beginning to grow, sticking together in the warm inner regions, remaining separate in the cold outer reaches. None of this will ever be seen by human eyes. The distance is too great, the events too slow, our instruments too limited. But we know it is happening, because we have seen it happening elsewhere, because the physics demands it, because every star in the sky was born this way, and every planet formed around such a star. The process that created us is still operating, still building new worlds, still setting the stage for possibilities we cannot imagine. There is a smaller, quieter story woven through all of this, one that rarely gets told. It is the story of failure. Not every core collapses to form a star, not every disk produces planets, not every planet survives the violent early history of its system. The universe is profligate with its experiments, starting many more than it finishes, discarding most of its attempts without ceremony. The clouds are full of cores that will never quite make it, that will be dispersed by passing stars or evaporated by ultraviolet radiation from nearby massive stars before they can collapse. The disks are full of dust that will never quite grow into planetesimals, that will be lost to the star through inward drift, or stripped away by stellar winds before it can be incorporated into a planet. The young planetary systems are full of protoplanets that will never quite finish forming, that will be ejected by gravitational interactions with their siblings, or consumed by the growing giant planets before they can settle into stable orbits. This is not tragedy. It is simply how the process works. The survivors are not the chosen ones, not the special cases, not the destined outcomes. They are the lucky ones, the ones that happen to be in the right place at the right time, the ones that avoided the many hazards that claim their siblings. Our solar system is not here because it was meant to be here. It is here because it happened to survive. And yet here we are, the products of this staggeringly unlikely sequence of events, able to look back and understand at least a little of how it happened. The universe is not impressed by our existence. It continues its business regardless of whether we observe it, or understand it, or care about it at all. But we are impressed by our own existence, or at least we should be. The chain of events that led from a collapsing cloud to a planet with oceans to beings with telescopes is improbable enough that it might never happen again in quite the same way. It is worth trying just once to feel the full weight of that improbability. Not as a reason for despair, not as evidence of cosmic indifference, but as an invitation to wonder. We are the universe examining itself, asking questions about its own origins, piecing together the story of how matter became aware. This is not a common occurrence. As far as we know, it may be quite rare. And the fact that it happened at all, that we are here at all, that we can look at light from a molecular cloud and understand what we're seeing, is itself a kind of miracle, even if it is a miracle without a miracle worker. The night deepens, the data continues to flow. Somewhere in Serpens, a protostar is still launching its jets, carving its channels through the dark. Somewhere in Chamaeleon, a disk is still spinning, its dust grains slowly drifting, slowly growing. Somewhere in the vast spaces between the stars, an atom of carbon or oxygen or nitrogen that will someday be part of a living thing is still floating, waiting, its destiny not yet decided. And we are here, in our houses and our beds and our lives, thinking about all of this, or not thinking about it, taking it for granted or marvelling at it, living our brief spans on this small world that emerged from all that chemistry and all that time and all that improbable luck. The universe does not need us to understand it, but we need to understand it, or at least to try, because that is what we are, what we have become, what the long chain of cosmic events has produced. Beings who ask questions about their own origins, who build telescopes to extend their sight, who look at the darkness and see not emptiness but possibility. There is something almost sacred about this enterprise, even for those who do not believe in the sacred. The pursuit of understanding, the patient accumulation of knowledge, the willingness to be surprised and to revise our beliefs in light of new evidence. These are among the best things we have learned to do. They do not promise certainty, they do not guarantee answers, but they offer something perhaps more valuable, the experience of honest inquiry, of looking at the universe as it is rather than as we wish it to be, of accepting what we find even when it overturns what we thought we knew. The molecular clouds do not care about our models. They continue their slow transformations regardless of whether we understand them. But our understanding matters to us. It changes how we see ourselves, how we relate to the cosmos, how we think about our place in the long story of matter and energy and time. Every observation that Webb sends back, every spectrum and every image adds a thread to this understanding. The tapestry is far from complete. It may never be complete, but it grows richer with every new thread, more beautiful, more true, and so we are left, as always, with questions. Not the urgent questions that demand immediate answers, but the quiet questions that can be held gently, turned over in the mind, contemplated without pressure. How did we come to be? Where did our atoms originate? What is the relationship between the cold chemistry of distant clouds and the warm complexity of life on Earth? These questions do not require solutions tonight. They are companions, not problems to be solved. They travel with us through our lives, growing deeper as our understanding grows, never quite resolving, never quite letting us rest. And perhaps that is exactly as it should be. Perhaps the deepest questions are not meant to be answered and set aside, but carried, like stones smoothed by long handling, like keepsakes from a journey that has no final destination. The questions themselves become the treasure. The asking becomes the gift. Consider for a moment what it means that we can ask at all. There was a time, not so long ago in cosmic terms, when no one was asking anything. The universe expanded and cooled and condensed and collapsed, following the rules written into its fabric, but there was no mind to wonder about those rules, no consciousness to notice the patterns, no creature to look up at the night and feel small and curious and alive. For billions of years, stars were born and died without witnesses. Galaxies collided and merged and spun their slow spirals through the dark, and it was all happening, all real, all present, but entirely unobserved. Then something changed. On at least one small world, and perhaps on others we have not yet found, matter organized itself into forms that could sense their surroundings, that could remember and anticipate, that could wonder. The universe, which had been proceeding blindly through its transformations, began to develop eyes, began to develop questions, began to develop that strange recursive capacity to examine itself, to ask how it came to be, to build instruments that could extend its newfound awareness across distances and timescales that would have been unimaginable to the first single-celled organisms floating in ancient seas. We are part of that development. Not the culmination, not the purpose, but a chapter in an ongoing story that began long before us and will continue long after. The atoms in your body were forged in the hearts of stars that lived and died before our sun was born. The complex molecules that carry your genetic information were first assembled in environments not so different from the molecular clouds Webb is studying now, cold and dark and rich with the raw materials of chemistry. You are, in a very real sense, a piece of the universe that has learned to ask questions about itself. You are stardust contemplating stardust. You are the cosmos made curious. This is not a metaphor, not a poetic flourish, but a statement of physical fact. The carbon in your cells, the oxygen in your blood, the calcium in your bones, the iron that carries breath through your body, all of it was synthesized in stellar furnaces, scattered by stellar deaths, gathered into new clouds, processed through new chemistry, incorporated into new worlds. The journey from there to here took billions of years and passed through countless intermediate states, from the hot plasma of supernovae to the cold silence of interstellar space, to the warm waters of a young planet to the intricate architecture of living cells. And at every step of that journey, the same fundamental processes were at work. Gravity gathering matter, chemistry transforming it, energy driving change. The universe is not random, but it is also not predetermined. It is creative, in the deepest sense of that word. It makes new things out of old things. It builds complexity from simplicity. It takes the same basic elements and arranges them into an endless variety of forms, some stable for billions of years, some lasting only moments, all connected by the threads of cause and effect that we are slowly learning to trace. Webb's observations of the molecular clouds are part of that tracing. When we look at the ices clinging to dust grains in Chamaeleon, we are looking at the starting materials of worlds. When we see the jets launching from protostars in Serpens, we are watching the birth pangs of new solar systems. When we measure the spectra of protoplanetary disks and find the signatures of complex organics, we are glimpsing the chemical heritage that will eventually be passed to any planets that form from those disks. This is not abstract science, disconnected from human concerns. This is the study of our origins, the investigation of where we came from and how we came to be. Every new discovery is a discovery about ourselves. Return with me one more time to the Serpens cloud. It is still there tonight, hanging in the summer sky for observers in the northern hemisphere, invisible to the naked eye but blazing with infrared light for any instrument sensitive enough to see it. The young stars embedded in its depths are still forming, still accreting material, still launching their bipolar jets into the surrounding medium. Nothing has changed in the few hours since we began this journey together. Nothing will change noticeably for thousands of years. The timescales of star formation are so long that human history is barely a flicker against them, a brief bright moment in an ongoing process that has been unfolding for billions of years and will continue for billions more. But in that brief bright moment we have learned so much. We have learned that the chemistry of star-forming regions is richer and more complex than we imagined, that the building blocks of life are present from the very beginning, that the seeds of planets and perhaps of biology are sown in the cold dark long before any sun ignites. We have learned that our models, carefully constructed over decades, need revision, that the universe is full of surprises, that we are still beginners in the project of understanding cosmic origins. And we have learned, perhaps most importantly, that learning itself is possible, that minds evolved on a small planet can reach out across vast distances and timescales and begin to comprehend processes that dwarf human experience by every conceivable measure. Spare a thought, too, for the instruments that make this possible. Webb is not just a telescope, but a culmination, the endpoint of a technological lineage stretching back centuries. Every mirror, every detector, every piece of sunshield fabric represents the accumulated knowledge of generations, the patient work of thousands of hands and minds, the slow accumulation of understanding that allows us to build machines far beyond what any individual could create alone. The first telescopes, simple tubes with lenses, showed us that the moon had mountains and Jupiter had moons, that the universe was larger and stranger than we had supposed. The reflecting telescopes that followed gathered more light, revealed more stars, suggested that the Milky Way was only one galaxy among many. The radio telescopes of the 20th century opened new windows on the cosmos, showing us phenomena invisible to optical light, hinting at the vast energies and processes that shape the universe on the larger scales. And now the infrared observatories culminating in Webb are revealing the hidden universe, the parts that glow in wavelengths our eyes cannot see, the cold, dark regions where the raw materials of stars and planets gather and transform. Each of these instruments was built by people who would not live to see all that their creations would discover. The scientists who first proposed Webb in the 1980s knew that they might not be alive when it finally launched. Many were not. They worked anyway, contributing their knowledge and their effort to a project that would benefit people they would never meet, revealing truths they would never know. This is a remarkable thing when you think about it. This willingness to invest in the future, to work for outcomes beyond one's own lifespan, to participate in an enterprise larger than any individual life. It is one of the best things about the scientific endeavour, one of the ways in which the pursuit of knowledge transcends the limitations of individual existence. The data that Webb is gathering now will be studied for decades. Astronomers not yet born will write papers about observations that are happening tonight, drawing conclusions that we cannot yet anticipate, fitting pieces into puzzles we do not yet know exist. The images and spectra and measurements will outlast every person currently involved in the mission, becoming part of the permanent record of human knowledge, available to anyone who wants to examine them for as long as our civilization endures. In this sense, the observations are not just scientific data, but a kind of inheritance, a gift from the present to the future, a message that says, "We were here, we looked, we wondered, and this is what we found." Let us sit for a long moment with that idea. The universe, as far as we know, does not preserve memories. Stars are born and die and leave no record of their existence, except the elements they scattered, the gravitational perturbations they caused, the light they emitted that may still be travelling through space. Galaxies merge and lose their individual identities, their histories blending into new configurations. Even the patterns of cosmic structure, the filaments and voids that we see in surveys of distant galaxies, are not memories but present states, snapshots of processes that have no awareness of their own unfolding. We are different. We remember. We record. We tell stories about what happened and what it meant and why it matters. We build archives and libraries and data centers, attempting to hold on to knowledge against the constant erosion of time. This is fragile, of course. Civilizations have risen and fallen and much has been lost. But the impulse to preserve, to remember, to pass on what we have learned, that seems to be as deep in us as the impulse to explore. We are the universe's memory, or one small part of it, a species that has developed the strange and wonderful habit of caring about the past and trying to ensure that something of value survives into the future. Webb's observations are part of that project. They're not just scientific measurements, but cultural artifacts, records of what we found when we looked at the universe with the best instruments we could build at this moment in our history. Future generations may have better telescopes, may see farther and understand more deeply, but they will still value what Webb showed us, just as we value the observations made by Galileo and Herschel and Hubble. Not because those observations are the last word, but because they are chapters in an ongoing story, steps on a path that continues to unfold. Picture, if you can, what that future might look like. A century from now, perhaps longer, astronomers may be studying star-forming regions with instruments we cannot yet imagine, making discoveries that would astonish us if we could know them. They will have access to Webb's data, will be able to compare their observations with ours, will trace the progress of science across the generations. They will know things we do not know, will have answered questions we cannot yet ask, will have their own mysteries and their own sense of wonder. And they will, perhaps, spare a thought for us, as we spare thoughts for those who came before, recognizing that the pursuit of understanding is a relay race across time, each generation carrying the torch a little farther before passing it on. This is the quiet miracle of science, if miracle is the right word for something that requires no supernatural intervention. The accumulation of knowledge across generations, the building of understanding piece by piece, the willingness to be wrong, to revise, to start again with better data and clearer thinking. It does not promise certainty or completeness. It does not claim to have all the answers or to be the only valid way of knowing. But it offers something precious, a method for distinguishing between what we hope is true and what actually appears to be true, a discipline for testing our beliefs against evidence, a tradition of honest inquiry that has proven remarkably effective at uncovering how the universe works. The molecular clouds are a good example. For decades, we thought we understood how star formation proceeded, how the chemistry unfolded, how the timescales played out. Our models were good models, based on careful observations and solid physics, consistent with the evidence available at the time, and then Webb came along and showed us that the evidence was incomplete, that there were processes we had not fully appreciated, that the real universe was more complicated and more interesting than our models had suggested. This is not a failure of science, but a success. The models were not wrong in the sense of being careless or dishonest, but in the sense of being incomplete, which all models are. The new observations did not invalidate the work that came before, but built upon it, adding new layers, revealing new complexities, driving the field forward. This is how understanding grows, not through sudden revelations that overturn everything, but through patient accumulation. The slow accretion of knowledge like dust gathering in a protoplanetary disk, each new grain adding to the mass, each new observation contributing to the picture. And we cannot leave this story without acknowledging the darkness. Not the physical darkness of the molecular clouds, which we have discussed at length, but the darkness of uncertainty, of not knowing, of standing at the edge of knowledge and looking out into the vast unknown. This is uncomfortable for some people, this recognition that our understanding is incomplete, that there are questions we cannot yet answer, that the universe may contain truths we have not yet glimpsed. But it can also be liberating. The darkness is not empty. It is full of potential, full of discoveries waiting to be made, full of wonders we have not yet imagined. Every great scientific advance began as a mystery, a gap in knowledge, a question without an answer. The darkness is where the future lives. Webb is extending the reach of human awareness into that darkness, one observation at a time. Every spectrum it records is a probe into the unknown, a test of our understanding, a potential source of surprise. The astronomers who analyze its data are not passive recipients of information, but active participants in a conversation with the cosmos, asking questions and listening for answers, proposing hypotheses and checking them against evidence. This is not a one-way process. The universe does not simply reveal itself to our inquiries. We must know how to ask, must have the theoretical frameworks to interpret what we see, must be willing to revise those frameworks when they prove inadequate. The conversation is ongoing, never complete, always productive of new questions even as it answers old ones. There is one more thing worth understanding, and it is perhaps the simplest thing of all. The universe is comprehensible. Not fully, not yet, perhaps not ever, but substantially, meaningfully, surprisingly. The same physical laws that govern matter on Earth govern matter in distant galaxies. The same chemistry that operates in our laboratories operates in molecular clouds light years away. The mathematics that we develop to describe local phenomena applies across cosmic distances and timescales. This is not obvious, not something we could have predicted from first principles. The universe could have been chaotic, different in every region, governed by local rules that varied from place to place. Instead, it appears to be unified, coherent, lawful in a way that makes understanding possible. We do not know why this is. Perhaps it is a deep truth about the nature of reality. Perhaps it is a necessary condition for existence. Perhaps it is just how things happen to be. But whatever the explanation, the fact remains. Minds that evolved on a small planet to deal with the practical problems of survival have proven capable of understanding processes that occur in the hearts of stars and the depths of space, and the moments after the beginning of time. This is astonishing. This is the quiet foundation beneath all of science, the assumption that makes inquiry meaningful, the gift that makes wonder possible. The night is very late now, or very early, depending on how you count. The molecular clouds continue their slow transformations, indifferent to our observations, following their own patient schedules. The protostars gather their mass. The disks swirl and settle. The jets punch through the darkness, carrying away angular momentum, clearing paths for the systems that will eventually emerge. And Webb watches, records, transmits its findings across the void to the waiting receivers on Earth, adding new pages to the book of cosmic knowledge that our species has been writing for centuries. You do not need to understand all of this tonight. You do not need to remember the details, the spectra, the chemical names, the timescales. What matters perhaps is simply the recognition that this understanding exists, that we are capable of it, that the universe is the kind of place where such understanding can develop and grow. You are part of that process, even if only as a listener, even if only as someone who wondered for a moment about the origins of stars and the chemistry of distant clouds. Your wondering matters. It is continuous with the wondering of the astronomers who build the telescopes and analyze the data, continuous with the wondering of the philosophers who first asked what stars were made of, continuous with the wondering of every human being who has ever looked up at the night sky and felt curious about what they saw. We are the universe's way of knowing itself. Not the only way, perhaps, if other minds exist elsewhere in the cosmos, but one way, one strand in a tapestry that may be far larger than we can imagine, and the knowing continues. Night after night, observation after observation, question after question. A slow, patient accumulation that has no definite endpoint, no final chapter, no ultimate revelation that will make further inquiry unnecessary. There is always more to learn. There is always another mystery beyond the one we have just solved. There is always, in the cold dark spaces between the stars, another cloud gathering, another star beginning, another world taking shape from the raw materials scattered by ancient deaths. This is the story that Webb is telling us, one infrared photon at a time. The story of cosmic origins, of chemical heritage, of the long, slow processes that lead from simple hydrogen to complex biology. It is our story, even though most of it happened before we existed and in places we will never visit. It is the story of where we came from and what we are made of, and how the universe operates when it creates new things from old things, and it is not finished. It will never be finished, as long as there are minds to ask questions and instruments to gather data, and patience enough to wait for answers. The clouds are still there tonight, the Serpens and the Chamaeleon and countless others we have not named, suspended in the darkness like thoughts not yet fully formed, like questions waiting to be asked, like futures not yet realized. They will be there tomorrow and next year and a million years from now, changing slowly, forming their stars and planets, contributing their threads to the ongoing tapestry of cosmic evolution. And somewhere, in some form, the inquiry will continue. The wondering will persist. The universe will go on knowing itself, through whatever minds and instruments develop to extend its awareness, across whatever distances and timescales lie ahead. This is the gift. Not answers, which are always provisional, but the capacity for questions which seems inexhaustible. Not certainty, which the cosmos does not provide, but wonder, which the cosmos endlessly inspires. Not completion, which may never arrive, but participation, which is available to anyone willing to look up and ask. Thank you for looking with me tonight. Thank you for wondering about molecular clouds and protostellar jets, and the chemistry of distant darkness. Thank you for being part of this brief moment in cosmic history, when minds exist to ask questions about their own origins. The universe is still making new stars. It is still making new worlds. It has not stopped creating, has not exhausted its potential, has not reached any kind of final state. And we are part of that creation, looking back at it, trying to understand it, marveling at the strangeness and the beauty of what we find. Keep looking up, keep wondering. Take care of one another, and of this small world that holds all the wondering minds we know of. The story continues, with or without us, but it is richer because we are here to witness it, to record it, to carry it forward for a little while. Sleep well. The clouds will still be there in the morning, slowly making something new out of something old, and so will we. Good night.